Hello, I'm Aiden.
And I'm Zachary.
We are Team Fusion Zero from New Zealand, competing in the RoboCup Junior Rescue Line International League. I am the team captain, lead programmer, and PCB designer. I mainly focus on line following, obstacle avoidance, intersection handling, and the main software structure of the robot.
I'm the lead hardware engineer. I focus on the physical construction of the robot, mechanical design, GitHub, and the evacuation zone.
Starting with the robot overview. Our new robot has a compact footprint of 180 by 149.4 millimeters. From my previous competition, we found that larger robots often struggle with tight turns, obstacles, and evacuation zone movement. Because of that, one of our main priorities was reducing the robot's footprint while still fitting all required systems. To achieve this, we used custom PCBs, custom sensor boards, 3D printed parts, and custom wheels. This lets us place components exactly where we need them instead of building around large modules or messy wiring. The main processor is now a Raspberry Pi 5. This gives us more processing power and better supports the camera-based parts of the robot. It also supports multiple CSI camera connectors, which is useful because the robot uses vision for both line following and evacuation. The Raspberry Pi connects to our custom 40-pin GPIO header shield. This gives us clean JST connections for sensors and modules, a 5-volt input, and more organized electronics layout. During testing, this makes debugging much easier because each module connects through a defined port instead of loose wires going everywhere.
The robot is powered by three 18650 batteries. Each cell has a nominal voltage of 3.6 volts, a maximum voltage of 4.2 volts, and a capacity of over 2000 milliamp hours. This gives us enough power for the motors, servos, sensors, and cameras, while keeping the battery system compact. For movement, the robot uses 4 Pololu micro metal DC motors. These are 6-volt motors with a 380 to 1 gearbox, around 85 RPM, and approximately 5 kilograms/centimeters of torque, giving us a strong and compact drive system for ramps, speed bumps, and uneven terrain. For the claw and dump mechanism, we use a DS servo RDS 3218 as the main lift servo. It has 270 degrees of movement, 20 kilograms/centimeters of torque. We also use a Tower Pro SG90 as the dump servo, giving 180 degrees of movement for sorting and releasing victims. The robot also uses a Xiao ESP32 as a supporting control board. It communicates through I2C and helps with servo connections and PWM generation. This reduces wiring complexity in the small robot body. For distance sensing, we use VL53L0X time of flight sensors. They communicate over I2C, have a range from around 30 millimeters to 2 meters, and can read in around 20 milliseconds. These are used for obstacle handling, wall following, centering in evacuation, and fine positioning near victims.
The robot also uses a GY BNO08X IMU, giving accelerometer, gyroscope, and magnetometer data. This helps the robot understand whether it's uphill, downhill, tilted, or crossing the seesaw. We also added an SSD1306 OLED display. It shows the robot's current mode, sensor readings, and state.
One important mechanical change this year is the custom WEG design. The outer diameter is 76 millimeters. The inner diameter is 70 millimeters. The outer material is A30 silicone, giving strong grip on ramps and uneven surfaces. The small cutouts are a compromise. A more aggressive WEG can help on speed bumps, but it can also make normal driving less smooth.
Our design process is iterative. We use CAD with parametric variables so dimensions can be changed quickly without rebuilding the whole model. We also use sub-assemblies and revolution mates to test moving mechanisms virtually before printing. Another design detail is the dump structure. The support beams use snug clipping mechanisms to reduce the number of screws needed. Where screws are used, they are placed across 2 axes instead of 1 plane. This holds the dump tightly while still making it easier to access the PCB. Moving on to line following, this is the section I mainly worked on. Each loop starts by reading the current sensor inputs, including the camera image, front touch sensors, distance sensors, and IMG state. The robot then chooses the correct behavior based on what it sees. For normal line tracking, the robot finds dark contours in the camera's frame. It filters them by area, height, and position, so random shadows or marks are ignored. If multiple contours are valid, the robot chooses the strongest one based on its size and shape. Once the line is selected, the robot calculates the line angle and adjusts the motor speeds. For smooth curves, it uses small corrections. For sharp curves, it turns more aggressively. This lets the same system handle both gradual curves and tight corners. If the robot loses the line, it treats it as a gap. Green intersections are handled separately. When green is detected, the robot waits until the marker is close enough before deciding. It then checks for black above the green, left, and right to decide whether it should turn left, turn right, or handle a double green. Obstacle avoidance uses the front touch sensors and time of flight sensors. When a touch sensor is triggered, the robot confirms the obstacle, follows a detour around it using the side sensors, then realigns once it finds the black line again.
Moving on to the evacuation zone, this is the section I mainly worked on. In evacuation, the robot uses a forward-facing camera to identify victims, evacuation points, and the entrance and exit areas. It also uses the gyroscope fused with laser sensors for wall following, positioning, and movement around the zone. At the start of evacuation, the robot checks the call state to decide what to search for next, depending on what has already been collected. It searches for live victims, dead victims, and the correct evacuation triangle. Live victims are tested using model confidence combined with reflective highlight validation. Dead victims are also detected using the custom model. Once a victim is found, the robot routes towards it. For drop-offs, it moves away from the walls, searches for the correct red and green triangles, realigns, and dumps the correct victims into the evacuation point.
Overall, the new robot is designed to be smaller, cleaner, and more reliable than our previous versions. The Raspberry Pi 5 gives us more processing power, the custom shield reduces wiring complexity, and the sensor layout gives the software more information to make decisions.
Mechanically, the custom legs, compact chassis, and improved core system are designed to handle the physical challenges of rescue line while staying easy to maintain and debug. In the future, we want to improve mapping in the evacuation zone and continue developing AI detection alongside our custom vision methods. This will allow the robot to verify targets more reliably and make better decisions during rescue. In the future, we want to improve mapping in the evacuation zone and continue developing AI detection alongside our custom vision methods.
This is Fusion Zero, a Robocop Jr. rescue line robot.
Thank you for watching.